وعليكم السلام ورحمة الله.
Do you see the distance formula? Sorry, do you see the one on screen?
Yes, we can see.
Yes, we can see.
Okay, next thing is distance between two points. Those 2 points can be in Cartesian. Points in this space are same, but they are represented by Cartesian coordinates or cylindrical coordinates or spherical coordinates. Then how do we compute? Either we convert the coordinates to Cartesian, which is a formula we are familiar with from our previous courses. Either we convert coordinates rho phi z into xyz or r theta phi into xyz and then use 2.3.1, or we can use directly formula 2.32 for the cylindrical and 2.33 for spherical. So if there is a question to find distance between 2 points, this formula should be given. Maybe not Cartesian, you are very well familiar with this one. But for cylindrical and spherical, this is a new formula for you. So this was one more thing we need to do. We did one complete example yesterday. There are some practice problems similar to what we have done. Yani what type of questions you will see for this chapter? A point is given. In one coordinate system, you need to convert it into other coordinate systems. A vector is given in one coordinate system, you need to convert into other coordinate systems. And you can also evaluate in the other coordinate systems. And 2 points are given, find distance between them. That is the simplest thing using these formulas. Also, last time we learned constant surfaces. In x, y, z, when x, y, and z are equal to some constant, then what do they represent? When rho, phi, and z are constant, what do they represent? When r is constant, theta is constant, or phi is constant, what do they represent? We learned this yesterday. There are, these things are also given by some figures. They are given in your book. For example, just for the sake of completeness, I can copy and paste this figure here. Coordinate surfaces. Instead of this one, for cylindrical coordinate surfaces, we can have this figure where you can see clearly. This is for the Cartesian, and this is the simplest one. This is the simplest one. Yeah, here, this one. is for cylindrical. And here clearly they are saying when rho is constant, we get a cylinder. When z is constant, we get a plane parallel to xy plane. And when phi is constant, we get a half plane whose one edge is on z axis. And similarly, this is figure given previous. So let me just erase this. And for spherical coordinates, this is a good figure. Let me put it here, where you can clearly see that theta constant is a cone, like what we have written here. R constant is a sphere, like what they are trying to show on the left hand side. And phi constant is a semi-finite plane, exactly same thing we have written here. So this is the figure which is telling us about these three surfaces when these variables r, theta, and phi are constant. Okay. What is more? There are some examples, more examples. Like example number 2.3, two uniform vector fields are given by this one. Okay, what is a vector field? A vector in space, a set of vectors in space, we call it as a vector field. Like you have, you know this, maybe not seen, you know this, or maybe you have seen this in some figures, two vector fields on the poles of a magnet. On the poles of a magnet. You must have seen vector fields I think somewhere in calculus. Vector field is a set of vectors in a coordinate system. So a vector field is also a vector. A vector in a vector field is a vector. Okay, in this example, what I'm seeing is to find their cross product vector component of one vector parallel to the line, this one, and the angle between the surface E with the surface Z equal to 3 at point P, blah, blah, blah. So let us do this example. Let me show you how to do this. It's not very difficult. Okay. Now, this is the example 2.3. Two unit vector fields are given, E and F. You can see that E vector is a vector in cylindrical coordinate system. F 1a rho plus 2a phi minus 6az is also a vector in cylindrical coordinate system. So here they are saying two uniform vector fields are given. So instead of saying vectors, we call them vector field. Now to find cross product, and magnitude of this. First, let us see revise how to find the cross product using the determinant. So first will be A sub rho, then A sub phi, then A sub z. The components of vector field or vector E, -5, 10, 3, 1, 2, and -6. So this is equal to -60, -6, -66 a row minus -10, -10. So -20, so plus 20 a phi is, oh, that was with a phi, a z, my mistake. With a phi, 30 minus 3 plus 30 minus 3, 27. So minus 27 a phi, and then -10 -10 minus 20 a z. So that's it. And finding magnitude, E cross F, magnitude is a -66 square plus -27 square plus -20 square, and then square root. You can use your calculator and calculate this number. Very, very easy. So we can say this is part A. Now let us do part B. Now in part B, it says the vector component of E at point P parallel to the line x equal to 2, z equal to 3. If you know from your calculus math 201 exercise 12.5, parametric equations of a line. Now x equal to 2 and y equal to 3. Actually, what are these two? These two are two planes. One plane x equal to 2, x equal to 2, a plane parallel to y z plane, and the other one is z equal to 3. So it is a vertical plane. Z equal to 3, a plane parallel to xy plane, and 3 unit above the xy plane. Above, usually we take xy plane parallel to the ground, so above, 3 unit above the ground. So this is one horizontal plane, one vertical plane. One horizontal plane here. You can just imagine by putting your two hands, one horizontal, one vertical, and where do they intersect? That will be a line. Any x equal to 2 and y equal z equal to 3. A line. Actually, it is a line of intersection. It is a line of intersection of two planes. One is horizontal and the other plane is parallel to XY plane, 2 units from XY plane. So what about Y variable in this line? This will be a line in which X always equal to 2, Z always equal to 3, and Y can take values from minus infinity to plus infinity. Yani Y is a free variable. So Y can take any value from minus infinity to plus infinity. I hope you get it, that how we are saying that X equal to 2 and Z equal to 3 is a line. Okay. Now, this vector E is equal to -5 a row plus 10 a phi plus 3 a z. This is a vector in 3D coordinate system. This is a vector in 3D coordinate system, yani in a space. There is a line. There is a line x equal to 2, z equal to 3 in this space in 3D coordinate system. Okay. And from the idea of vector projection, from the idea of a vector projection, you know, you have seen two types of vector projection, a scalar projection and a vector projection. Let me just quickly remind you. So we say that projection of a vector A onto vector B or in the direction of vector B is A dot B over magnitude of B. Now multiply a unit vector in the direction of B, and a unit vector in the direction of B is a vector B divided by its magnitude. Okay, is divided by its magnitude. And if we do not have this one, this quantity, then what you are seeing here, this is called a scalar projection. And we convert it into a vector projection by multiplying with this magnitude. We can write this as A dot unit vector B, A dot unit vector B, and multiply by unit vector B. You remember, this is a scalar. This is a scalar. So A dot B, here I should change the notation. Because now we are saying this one. So A dot B hat multiply unit B hat, where B hat is vector B divided by magnitude of vector B. So A dot B hat, scalar quantity, and multiply with B hat. This is what? If you are taking a projection of vector A onto vector B. We also call it as projection of vector A in the direction of vector B. And this is a vector projection because a result of this is a vector. And if we have the other projection, which we call as a component only, and that will be, actually in that book we say a component and a vector projection. And a component is with, or we can also say whatever this is, let's say vector V. And we call this vector A equal to A1I plus A2J plus A3K, and vector B is equal to B1I plus B2J plus B3K. If we call them this one, then one component will be only, yes?
Isn't B is vector B over the magnitude squared? Not the magnitude.
Yeah,
Right.
this become magnitude square, but we keep them separate, and we call B over B magnitude as B hat and other B over B magnitude as B hat. It will become magnitude square if we do not write into this form.
Oh, okay.
Okay.
I get you now.
So this is from your calculus. I was just trying to remind you. What is here? Instead of IJK, we use different notation. And part B here, you can see that the vector component of E parallel to the line, yani in the direction of this line. And we know that this line is, this x equal to 2 and z equal to 3 is a line in the y direction, any along y-axis, parallel to y-axis, in the y direction, or say parallel to y-axis. In the bracket, I'm saying parallel to y-axis, not on y-axis, parallel to y-axis. Okay. So this component is equal to vector E dot a unit vector in the direction along on which you are taking the projection, and we are taking projection onto y-axis or parallel to y-axis. So we will take a unit vector. We will take a unit vector in the y direction and multiply by a unit vector in the y direction. This y is same like vector unit vector b hat. This ay is same like we have b hat before. And this vector e is the same like vector a we have before. I explain you this. Okay. But we need to compute this ay, since vector E is in cylindrical coordinates and ay is in Cartesian coordinates. So transform or convert AY into cylindrical. Convert A sub Y into cylindrical coordinates. And we have seen before, long before, that this is equal to sine phi A rho plus cosine phi A phi. There will be no Z component because line is not going up or down. Okay. At the point, what is given here, at the point 5 pi over 2 and 3, at P 5 pi over 2 and 3, this vector AY, unit vector AY, it will be, there is no rho here, pi over 2, sine pi over 2 is 1, so this is a rho only, and plus cosine pi over 2 is 0, so 0 a phi, so it is equal to a rho only. Okay, so AY vector A, unit vector AY is equal to unit vector A rho. At this point, you change the point, that answer will be different. At pi over 2. You know, this pi over 2 is angle phi. Do you know this? And angle phi starts from where? From positive x-axis. And when angle phi is pi over 2, then the point is where? On which axis? Y-axis. So this is the reason we have a rho. AY is a rho. So now we can compute E dot AY unit vector and unit vector AY in the direction of this one is equal to E dot A rho and A rho. What is the rho component of vector E? It is negative 5. So E dot A rho will be negative 5 and then outside A rho. So we have this as the component of vector component of E in the direction of Z equal to 3 and X equal to 2 line, which is a line parallel to Y axis in the Y direction. And when we convert this AY into cylindrical by this equation, we get AY equal to a rho, and the reason that we get a rho only, no a phi, because at pi over 2 cosine phi is 0. And also I told you that the phi angles start from positive x-axis, and when phi is pi over 2, we are on y-axis, and this is the reason we get a rho same as a y. So this was the second part of the question. Now let me see what is third part of the question. The angle E, the angle which vector E makes with the surface Z equal to 3. Now this at the point P. At point P, the vector E is making some angle with Z axis. Sorry, Z equal to 3 plane. Z equal to 3 plane. Z equal to 3 plane is a plane parallel to XY plane. So what angle is between vector E and XY plane is the same as angle between E and Z equal to 3, Z equal to 3 plane. Now we need to compute this angle at point P. So let us see how we do this. Since Z-axis is normal to the surface, you know the word normal, perpendicular. What is normal to XY plane? Z-axis is normal to XY plane. And what is a unit vector normal to XY plane? A sub Z, or this one, let me write. This is a unit vector normal to XY plane, and before we were using K hat, perpendicular to the surface. So Z-axis is normal to the surface at Z equal to 3. And you know that how we can find angle between two vectors, vector A, vector B. Do you remember? A dot B is equal to magnitude of A, magnitude of B, and then cosine of the angle between them. You remember this?
Yes.
Yes. So the same idea we will use here. So first find angle between vector E and AZ. So first find angle between E and AZ. So for this, and luckily or yani by chance, AZ is same in Cartesian coordinates and AZ is also in cylindrical coordinates. So for this, we will find E dot AZ. Oh, I'm putting vector notation. Oh yeah, it is better to put a vector notation because book is making it bold and we cannot make it bold. So let me do it here also. So it is better if we put a vector notation on these vectors. And that is equal to what? Magnitude of E, magnitude of AZ, cosine of the angle, and we call it, book is calling it as theta EZ. So not theta, not phi, let us call this as psi, where psi is angle between E and psi. It is angle, come on, between vector E and unit vector AZ. And cosine of psi, E dot AZ. Can someone tell me what will be E dot AZ?
-6.
E dot AZ.
9.
E dot AZ, yes. Three. So E dot AZ is 3 because we can write AZ as 0, 0 a rho plus 0 a phi plus 1 AZ. And when we take dot product, Dot product of AZ with A row is 0. Dot product of AZ with A phi is 0. Dot product of AZ with AZ is 1. So what's left is just 3. Divide by magnitude 74.06. 74.06 magnitude, and magnitude of AZ is 1. So what we are left with, this thing. Magnitude of E. Oh, sorry, this is not true. This is the magnitude of the cross product. What is a magnitude of E? E is what? 5, 10, 3, 100, 25, 39, 35, 34. So 134 square root psi is equal to, when you calculate this, 3 over 134 square root, and then take cosine inverse of this 3 over 30. This is 0.2592, and when we compute this and convert into degrees, we get 74.98, and this step you can do by your calculator. That is not difficult. So here I try to explain you things. I try to explain the steps which were a kind of missing. Like how component is E dot AY, multiply unit vector AY, and then angle between two vectors from your calculus. Here it should be arrow here. So, and the figure is also given in your book. Then there is some practice problem 2.3, something similar solved here. So let me just leave that for you guys, and practice problem 2.4. And a MATLAB code is given. You do not need to worry about this MATLAB code. And that's it. Now we have exercise. In exercise, you have different type of questions. And I think in the syllabus, we also mentioned some questions from this exercise, chapter 2, 2.5, 2.7, 17, 18, 19, 20. So these are some questions which you need to solve. Like if you have book, you can open that book. One question is a Cartesian is given, and then they ask which one is correct. Rho equal to 5, you can compute rho, and then if it is 5 or not. Theta, compute r, compute phi, and tell which one, which is correct, which is not correct. So that is conversion of a point from one coordinate system to the other coordinate system. And similarly, other questions. Try to solve as many as you can. So also here, first set is the review questions, then second set is actually the exercise problems. Convert this point into the other coordinate systems, and then transform one vector to another vectors in other coordinate systems like we did before. So hopefully you will not see a question where it has some new idea. So try to solve these problems similar to the examples we did. You must first try to solve the solved examples, make them clear in your head. Also, you solve the practice exercises, problems, make them clear what they are doing and why they are doing. If something is not clear, I'm here to help. And then you can go to exercise and solve questions from exercise. Now, according to syllabus, can you hear me now, Shabab?
Yes, we can hear you.
Yes.
Actually, there was a lag where you could not
We
hear
were
me.
here.
Sorry?
We were hearing you all the time.
Oh, okay. Now, the next thing we have, according to our syllabus, chapter 3, we will start this week and we will continue next week. Also, a little part next week. And that is chapter 3. Chapter 3. What is chapter 3? Vector calculus. Section chapter 2. And now I'm adding new one. Section chapter 3. Actually, the file which I uploaded, it has a name chapter 2. So just to make it different, I'm saying section chapter 3. Similar to the previous ones. Okay. What is this? Vector calculus. The first section is just some few lines introduction. So here is also in this chapter, there are different sections. So just to remember, let me put these also. And not only with this one, with the previous chapter 2, you can open your book and wherever some sections start in, you can also write a comment over there that from here it is section 2.2, section 2.3, section 2.4 according to the book. Now, what is this section 3.2? Differential length, area, and volume. Differential length, area, and volume. Okay, first of all, in Cartesian coordinate system, Cartesian coordinate system. So whatever I write in red color, underline it. It is a kind of section heading or some heading. Now in Cartesian coordinate system, suppose that we have 2 points, or let's say a vector. We have some vector. Or from one point, we go to the other point in a straight line. Like, let me try to write this one here. So here, this is x-axis, this is y-axis, and this is z-axis. Okay, instead of this one, let me just make it. That is better, because we are more used to of this one. Seeing x-axis, y-axis, and z-axis like this one. X-axis, y-axis, and z-axis. Now we move from this point to another point in space. We go from one point to another point in space. Not necessarily parallel to x-axis or y-axis or z-axis. We go from one point S to another point B in space, where S is some x comma y comma z, and B is x and little change in x, y and little change in y, and z and plus dz, z plus dz. A small change in x, small change in y, small change in z. You know from your calculus that we denote a small change by dx or dy or dz. Now when there is a small change in x, small change in y, small change in z, then there will be some change. When you move from x to z, b, s to b, when you go from s to b, when there is a little change in the point s, and after change we go to point b, then in the length, there is also some little change, and that is denoted by dl. Now dl is equal to, when we in this space, when we go from one point to the other point, and let us say we make some vector from one point to the second point, then it has one x component, one y component, one z component. It has x component, y component, and z component. And what will be change in, like for example, I will come back to this one. Suppose, just to explain you this, suppose we are in 2 dimension. So this is x-axis, this is y-axis. Now when we go from S to B, we go from here and then here. Now this, suppose this is vector SB, this is vector, this is vector. So this vector will be x component, yani x dx a. How do we compute vector from S to B? X plus dx minus x. So what's left is dx. Dx ax, yani how much is the change? And here how much is the change? dy, and a unit vector in the y direction. So this vector from S to B is equal to dx ax plus dy ay. Okay, this small vector from S to B. So the similar thing is when, now let me go back into the original figure, the previous figure. This one. So for this small change, this length, this small dl it will be equal to dx a sub x plus dy a sub y plus dz and unit vector az. So this is called differential displacement. Differential displacement. We displace from one point to a neighboring point. In the displacement, what is a little change? dl. And what is this dl equal to? dx ax, dy ay, dz az. Now the second thing is displacement in the surface area. Suppose that's a three-dimensional box. Instead of making this figure, let me copy and paste from the book. That will be easy for me. That will be easy for me. I can, instead of making this, I can copy and paste and then save my time. And that time I can use for explaining. Okay, now here we have a surface S. A surface S. Now, this surface has 1, 2, 3, 4, 5, 6. 6 faces. 6 faces. A, B, C, D is one of them. And A, B, C, D has a vector which is perpendicular to A, B, C, D, and that is A sub x. And what about PQRS? PQRS, that is other side face. Can someone tell me what will be the unit perpendicular unit vector on PQRS? Negative A sub x. Yani it is in the opposite direction of x-axis. So it will be negative ax. A unit vector which is perpendicular to the face PQRC will be, this time I will wait.
A sub y.
A sub y, excellent. A sub y. So similarly, for every face, what do we have? We have a unit normal. Now, when size of this cube or this box increases, then let me ask you first. Okay, what is this face A, B, C, D? Face A, B, C, D. This is y multiply z. Y value, or you can say that this is, what is this length DC, which will be some distance along y-axis DC multiply perpendicular vertical distance AD. You know AD and BC are equal, and DC, AD, BC are equal. DC and AB are equal. So we write DC multiply AD. So this is this face, which we can call that as Y length and Z length. Okay. Now when this size of this surface increases, changes, then how much will be the change ds? You know, the faces which have perpendicular in the x direction, like ABCD or PQRS, this face will increase. How much this face will increase? How much is in change in y and how much is change in z? So this is only the increase. This is only the increase, and this is increase is perpendicular to a sub x. Now here a sub x is a normal vector, because for a surface we do not have a unique parallel vector, so we have normal vector. So small change ds will have this much change parallel to xz plane, parallel to yz plane. Similarly, how much change will be parallel to AY, parallel to xz plane? It will be dx, dz, and AY. Plus the third one, parallel to, or when we have this normal along z-axis, then it will be dx, dy. So this is the differential. This is the differential. Any little change in the surface area, small change in the surface area, and it is written as three components. How much is change in each, let us say, direction? Yani how much is change parallel to each coordinate plane? We have three coordinate planes: xy plane, yz plane, and zx plane. These are three coordinate planes. And how much is the change parallel to those planes? It is given by this one. Okay, and AX is a unit normal to YZ plane. AY is a unit normal to XZ plane. AX is a unit normal to AZ is a unit normal to XY plane. These are three planes. It is 10:19. So now it is time for me to stop here, and I will continue tomorrow, inshallah, from this point. Now, we should have our next quiz on Sunday, and previous quiz was up to 8.10, yani orthogonal matrices. Then after that, we have diagonalization. Diagonalization is also similar to the previous material, that is easy. So let us have our quiz on Sunday, and we have many days before that. We have tomorrow Wednesday, Thursday, Friday, Saturday, 4 days before that. And I hope you can prepare chapter 2 in 4 days. So let us have our next quiz from chapter 2. Prepare it well, like you have to prepare it for your midterm exam. And if you want, we can have some special session, help session, where I can explain you or I can answer your questions. So our next quiz will be from chapter 2. Any question?
8.12 is not with us, right?
8.12?
Yeah, it's not with us in the quiz.
No. 8.12 is diagonalization. It is very similar and easy and a small exercise. So